A related topic to specific heat type of processes in calculating the heat involved in changing temperature is something called calorimetry. And this is based on the fact that both the system and the surroundings are changing, right? So if the system is releasing heat to the surroundings, both are going to change temperature. And if the surroundings are adding heat to the system, both are going to change in temperature. And often I can use calorimetry if I know something about either the system or the surroundings to do some calculations about the other process that I'm interested in but I don't have access to. So for instance, if I know what's happening to the surroundings, I know by energy conservation what's happening to the system. And if I know what's happening to the system, I can use energy conservation to know what's happening to the process of the surroundings. Again, we said when a hot sample is adjacent to a cold sample or a cold surroundings or vice versa, then heat must be conserved, and so the hot object will be losing heat energy and transferring it to the cold object. So the energy lost by the hot object has to be equal to a negative in sign times the energy gained by the cold object. And therefore I can now, depending on what type of heat process it is, whether it's a change in temperature or a change in state or a change in reaction, I can now set up an equation. I do need to be careful about understanding which one is the one that's losing energy and which one is the one that's gaining heat energy. But if I put a hot metal, then the hot object of the metal would be the thing that's losing energy, and if it was just a physical change of changing temperature, my Q equation would be mass times specific heat times the change in temperature. Similarly, the cold water would be the cold object that's gaining the heat, and I would have a negative sign times the energy, the heat energy of the cold water gaining, which is the mass times the specific heat times the change in temperature. Note that the final temperature happens when they reach thermal equilibrium, and so these are the same value. The temperature final for the hot metal will be the temperature final for the cold water. And we would expect that. If I put a hot metal in a cold water and I wait till they've equilibrated, they're now all at the same temperature. So if I can use this to figure out the thing that I don't know. Oftentimes we're looking for what is the specific heat of the metal, but it also might be if this is no longer the heat energy lost by a hot piece of metal, but the heat energy lost by a chemical system in a chemical reaction, I can use calorimetry to determine it. Here's a sample problem. We can work this one in our session in class, so I'm going to skip it. Related to calorimetry is heat of vaporization and heat of fusion. And these are ways to deal with energy, the heat energy involved in changing state. So heat of vaporization is the amount of heat energy required to convert 1 gram of substance, and sometimes it's 1 mole of substance. I have to have different reference tables I can refer to, going from liquid to vapor with no temperature change. The heat of fusion is the amount of heat energy required to convert 1 gram of substance from solid to liquid. So heat of vaporization is applying to the boiling process. Heat of fusion is talking about the melting process. These are going to be values that change with different substances, and I can use this. So here all I need to know is how much substance I have. There is no temperature change, so I just need to know what is the heat of vaporization and how much substance do we have. I could calculate how much heat is needed to turn 56 grams of liquid water into steam, and here I'd have my mass is 56 grams. I'd have to look up the heat of vaporization of, this would be the heat of vaporization of water, and I get 127 kilojoules. If I asked about 56 grams of liquid water turning into ice, this is now a freezing process. Remember, this is liquid water turning into ice. This should be a negative process. I missed the negative sign. Because it is liquid going into ice, this is freezing, and that's a energy releasing process, so this should be a negative value. It does say how much heat is released, and so that's why it's missing the negative sign. Sorry, I messed that up. So this is correct. 18.7, because this word released refers to what is the negative Q, and therefore I'm calculating it as if it's a positive number. So when we're working these state change problems with heat of fusion and heat of vaporization, it's important that I know that I actually have to be changing state, and that can only occur at the melting point and the boiling point. So I have to make sure it's happening at the proper temperature for it to be occurring, and which one I use will depend on if the process is an energy releasing or an energy absorbing process. So the boiling equation is Q is equal to the mass times the heat of vaporization, but the condensing, which is the reverse process, I have a negative sign in front. Same thing with melting and freezing. And again, I'm going to have to look up those values. If I don't know the heat of vaporization or heat of fusion for a substance, it may be something I have to go to a reference table for.